Article 310.13b2 addresses the ampacity adjustment factors for current carrying conductors in a raceway. When the number of current carrying conductors in a raceway exceeds 3, the allowable ampacity of each conductor must be reduced as shown in Table 310.15b2a. This adjustment is crucial to prevent overheating and ensure electrical safety. To determine the number of number 12 THHN current carrying conductors that can be in a 2-inch conduit going to a 20 amp circuit breaker, several steps must be taken. Firstly, you need to determine the total number of current carrying conductors. The NEC requires ampacity adjustment when there are more than 3 current carrying conductors in a raceway or cable. Without knowing the exact number of current carrying conductors, a precise calculation cannot be performed. Let's assume for illustrative purposes that you have 5 current carrying conductors in the conduit. Secondly, identify the adjustment factor. Once you know the number of current carrying conductors, you can use Table 310.15b2 in the National Electrical Code to find the corresponding adjustment factor. For 5 current carrying conductors, the adjustment factor is 0.80. This means that the allowable ampacity of each conductor must be reduced to 80% of its original value. Thirdly, calculate the adjusted ampacity. To calculate the adjusted ampacity, multiply the conductor's original ampacity by the adjustment factor. For number 12 THHN copper conductors, the ampacity is typically 30 amps based on the 75 degrees Celsius column of Table 310.16. Therefore, the adjusted ampacity would be 30 amps multiplied by 0.80, which equals 24 amps. Fourthly, determine the circuit breaker size. The circuit breaker is sized to protect the conductors from overcurrent. The adjusted ampacity is 24 amps. A standard 20 amp circuit breaker is appropriate, as it is the next lower standard size. Standard breaker sizes include 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, 100, 110, 125, 150, 175, 200, 225, 250, 300, 350, 400, 450, 500, 600, 700, 800, 1000, 1200, 1600, 2000, 2500, 3000, 4000, 5000, and 6000 amps. It is crucial to know the number of current carrying conductors in the raceway to accurately determine the adjustment factor and ensure the conductors are adequately protected by the circuit breaker. The NEC defines a current carrying conductor as a conductor that carries current under normal conditions. This typically includes the ungrounded or hot conductors and, in some cases, the neutral conductor. The neutral conductor is considered a current carrying conductor when it carries a significant amount of current, such as in a 3-wire circuit where the major portion of the load consists of nonlinear loads. Grounding conductors and equipment grounding conductors are not considered current carrying conductors for ampacity adjustment purposes. To accurately apply the ampacity adjustment factors, you must first identify all the current carrying conductors within the raceway. This includes all phase conductors and any neutral conductors that meet the criteria for being considered current carrying. Once you have determined the total number of current carrying conductors, you can consult Table 310.15b2 in the NEC to find the corresponding adjustment factor. This table provides adjustment factors based on the number of current carrying conductors in the raceway. The adjustment factor is a percentage by which you must reduce the allowable ampacity of each conductor. For example, if you have 7 current carrying conductors, the adjustment factor might be 0.70, which means you must reduce the ampacity of each conductor to 70% of its original value. After obtaining the adjustment factor, you must calculate the adjusted ampacity for each conductor. This is done by multiplying the conductor's original ampacity by the adjustment factor. For example, if a number 12 THHN conductor has an original ampacity of 30 amps and the adjustment factor is 0.70, the adjusted ampacity would be 21 amps. This means that the conductor can now only safely carry 21 amps in the given conditions. The circuit breaker or fuse protecting the circuit must be sized appropriately based on the adjusted ampacity. The overcurrent protection device should not exceed the adjusted ampacity of the conductors. In the previous example, where the adjusted ampacity is 21 amps, a 20 amp circuit breaker would be the appropriate choice, as it is the next lower standard size. Using an overcurrent protection device that is too large can lead to overheating and potentially dangerous conditions, such as fires. It is also essential to consider the temperature rating of the terminations and equipment connected to the conductors. The ampacity of the conductors must be selected based on the lowest temperature rating of any connected termination, conductor, or device. For example, if the terminals on a circuit breaker are only rated for 75 degrees Celsius, you must use the 75 degrees Celsius ampacity of the conductor, even if the conductor itself is rated for a higher temperature. This ensures that the connections do not overheat, which can lead to failures and safety hazards. In addition to ampacity adjustment factors, it is also important to consider conduit fill limitations. The NEC specifies the maximum percentage of a conduit's cross-sectional area that can be occupied by conductors. These limitations are in place to ensure that there is adequate space for heat dissipation and to prevent damage to the conductors during installation. The conduit fill limitations vary depending on the type of conduit and the number of conductors. For example, for 3 or more conductors in a conduit, the maximum fill is typically 40%. This means that the total cross-sectional area of all the conductors in the conduit cannot exceed 40% of the conduit's internal area. To determine the appropriate conduit size, you must calculate the total cross-sectional area of all the conductors. This can be done by referring to tables in the NEC that provide the cross-sectional area for different conductor sizes and types. Once you have the total cross-sectional area of the conductors, you can compare it to the conduit fill limitations to determine the minimum required conduit size. It's important to note that these calculations can be complex, and it is always best to consult with a qualified electrician or electrical engineer to ensure that the installation meets all applicable codes and standards. Furthermore, the type of insulation on the conductors affects their ampacity. THHN conductors are commonly used due to their high temperature rating and resistance to moisture. However, other types of conductors, such as THW or XHHW, may be used depending on the application and environmental conditions. Each type of conductor has a different ampacity rating, which must be considered when selecting the appropriate size and type of conductor for a given circuit. When running multiple circuits in the same conduit, you must consider the combined effect of all the current carrying conductors. The ampacity adjustment factors apply to all conductors in the conduit, regardless of whether they are part of the same circuit or different circuits. This means that if you have multiple circuits sharing a conduit, you must calculate the total number of current carrying conductors from all the circuits and apply the appropriate adjustment factor. In summary, determining the number of number 12 THHN current carrying conductors that can be safely installed in a 2-inch conduit protected by a 20 amp circuit breaker requires careful consideration of several factors. This includes firstly the number of current carrying conductors, secondly the ampacity adjustment factors, thirdly the temperature ratings of terminations and equipment, fourthly the conduit fill limitations, fifthly, the type of conductor insulation. Sixthly, the combined effect of multiple circuits. By following these steps and consulting the NEC, you can ensure that the electrical installation is safe and compliant with all applicable codes and standards. Remember, electrical work can be dangerous, and it is always best to consult with a qualified professional if you are unsure about any aspect of the installation. The NEC is updated regularly to reflect changes in technology and best practices. It is important to stay up to date with the latest edition of the NEC to ensure that your electrical work meets the current standards. The NEC is not a substitute for proper training and experience, but it provides a valuable resource for ensuring electrical safety. Properly deryting conductors is one of the most vital parts to electrical work. That is why it is so important to take into consideration. Improperly deryted conductors will quickly become an issue as the conductors get hotter due to higher amperage and resistance, increasing fire potential. As previously stated, a number 12 DHHN has an ampacity of 30 amps, but in this situation we need to lower that rating as a result of the conductors bundled together in a conduit. The 2023 NEC section 310.15 code states that you shall use the 90°C ampacities for ampacity adjustment and correction. Then, the conductor shall be limited to the temperature rating of the termination in accordance with 110.14 C. The purpose of directing conductors in a conduit is to prevent overheating and potential damage to the insulation of the wires, as well as to reduce the risk of fire. When multiple current-carrying conductors are grouped together in a conduit, the heat generated by each conductor can raise the overall temperature within the conduit. This increased temperature can reduce the ampacity of the conductors, which is the maximum amount of current they can safely carry. By directing the conductors, you are essentially reducing their allowable ampacity to account for the increased heat within the conduit. This ensures that the conductors do not overheat and that the electrical system operates safely and reliably. The amount of directing required depends on several factors, including the number of current-carrying conductors in the conduit, the ambient temperature, and the type of insulation used on the conductors. The NEC provides tables and guidelines for determining the appropriate directing factors for various situations. In addition to directing conductors for ampacity, it is also important to consider the fill capacity of the conduit. The NEC specifies the maximum percentage of the conduit's cross-sectional area that can be occupied by conductors. This is to ensure that there is adequate space for heat dissipation and to prevent damage to the conductors during installation. Overfilling a conduit can restrict airflow and increase the temperature within the conduit, which can further reduce the ampacity of the conductors. The fill capacity of a conduit depends on the type of conduit and the number of conductors it contains. The NEC provides tables and guidelines for determining the appropriate fill capacity for various situations. When selecting conductors for an electrical installation, it is important to consider both the ampacity of the conductors and the voltage drop. The voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The amount of voltage drop depends on several factors, including the length of the conductor, the current flowing through it, and the size of the conductor. The NEC provides guidelines for calculating voltage drop and for selecting conductors that will minimize voltage drop. In general, larger conductors will have less voltage drop than smaller conductors. Therefore, it is important to select conductors that are large enough to handle the expected current and to minimize voltage drop. When working with electrical systems, it is important to follow all safety precautions and to comply with all applicable codes and regulations. Electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are unsure about any aspect of the installation. The NEC is a comprehensive set of standards for electrical installations, and it is important to be familiar with its requirements. The NEC is updated regularly to reflect changes in technology and best practices. It is important to stay up to date with the latest edition of the NEC to ensure that your electrical work meets the current standards. In addition to the NEC, many local jurisdictions have their own electrical codes and regulations. It is important to be familiar with these local requirements as well. When planning an electrical installation, it is important to consider the future needs of the system. It is often wise to install larger conductors and conduits than are currently required in order to accommodate future expansion or changes in the load. This can save time and money in the long run, as it may avoid the need to replace conductors or conduits later on. Finally, it is important to document all electrical work that is performed. This includes keeping records of the conductors used, the conduit sizes, the circuit breaker ratings, and any other relevant information. This documentation can be helpful for troubleshooting problems in the future and for ensuring that the electrical system is properly maintained. When performing electrical work, it is important to use high-quality materials and equipment. This will help to ensure that the electrical system is safe and reliable. It is also important to use the correct tools for the job. Using the wrong tools can damage the electrical system or cause injury. When working with electrical systems, it is important to be aware of the potential hazards. These hazards include electric shock, arc flash, and explosions. It is important to take precautions to protect yourself from these hazards, such as wearing appropriate personal protective equipment and energizing circuits before working on them. Remember, safety is always the top priority when working with electrical systems. If you are ever unsure about how to perform a task safely, it is best to consult with a qualified electrician. Electrical safety is everyone's responsibility. By following safe practices and complying with all applicable codes and regulations, you can help to prevent electrical accidents and injuries. Electrical systems are an essential part of our modern world. By understanding how electrical systems work and how to work on them safely, we can help to ensure that they continue to provide us with the power we need to live and work.